Okay, folks, let's get started. So what we will be doing today is talking about some of our recent work on profile-based privacy. So this is a talk about privacy aspects of federated learning. And as you know, privacy, you must have seen that privacy is very much in the news now. And there are a lot of additional, there are a lot of recent privacy challenges that have been around. And what I work on in my group is basically looking at privacy modeling and definitions. We look at some practical problems and we try to come up with rigorous privacy guarantees and formalisms for these problems and design mechanisms that satisfy this formalism. Okay, the state of the art here is that there are quite a few concrete applications. That the 2020 census and differential privacy comes to mind, but Apple has been using differential privacy, a form of local differential privacy, for its usage statistic reporting. Private federated learning is of great importance to Google, and there are many emerging privacy challenges as well. Right, and some of these challenges have somewhat ad hoc solutions, and what we are hoping to do in my group is to look at some of these problems and come up with formal privacy solutions for many of them. Okay. So in this area, there are two styles of rigorous privacy definitions. The first is, differential privacy, but differential privacy actually came later. The second is inferential privacy. Okay, and so inferential privacy, and I'm citing Kiefer and Machanavajala 12 for inferential privacy, but because they really, nicely and cleanly formalize the definition. But this kind of idea has been in use in the literature for a very long time, way before their paper. And the idea here is as follows. You have an adversary which has some sort of prior knowledge. There is some private release based on some sensitive data. And based on this private release, the adversary updates their posterior knowledge, right? And privacy comes when the posterior of the adversary is more or less equal to its prior, right? So the adversary does not gain certain kinds of, does not gain a lot of knowledge once it sees the output of the private, once it sees this private release, okay? And, the advantage is that this sounds very natural. The disadvantage is that the guarantee that you can give for these kinds of things are highly dependent on the adversary classes, right? So if you have adversaries with different amounts of prior knowledge, then they could learn more, and there is not much that you can do about it. Right. However, the advantage again is that you can deal with, this kind of a privacy guarantee. You can deal with hiding certain things and not others, right? And which can be a problem in certain applications. For example, when you are talking about one person's data or, very small groups, and you're trying to, so you can't hide within the crowd, and you're trying to hide certain things but not others, right? In certain applications, you wish to do things like this. And there, this kind of guarantees can be quite important. Okay. And now differential privacy, which is kind of accepted as, one of the gold standards for private data analysis these days. Here, the guarantee is very different. The guarantee says that the participation of a single person in the data does not change the confidence of the adversary in any outcome. So if you have an algorithm which takes in some data set plus Alice, and it makes some, predictions, if you replaced Alice by Bob in the data, then its prediction will not change too much, right? And here the thing to note is that the only reason that this algorithm can be useful is because aggregation, right? So you are in some sense hiding within the crowd, so this is, the kind of thing that you need to do for differential privacy. Okay. So in this talk, what we will be doing is we will be talking about a certain form of inferential privacy called profile-based privacy that we have introduced. Okay. So before I go into profile-based privacy, let me talk about two different styles of models of privacy: local privacy versus centralized privacy. In centralized privacy, what happens is that you have a whole bunch of users which contribute their raw data to a curator. The curator aggregates the data, it comes up with some output, and then it does some sort of sanitization to the output. So the privacy barrier is between the private curator and the output, right? And an example of this sort of thing is, for example, census, right? You are supposed to report your raw outcomes to the census. You are supposed to legally bound, you're legally bound to do this. And then when the census releases its tables, it does some it does some sanitization. So for example, in 2020, they are going to do the sanitization with differential privacy. Okay. An alternative model, which has been quite useful, especially in industrial applications, is what is called local privacy. In this case, what happens is that there is no trusted curator, right? So you have your phone. Your phone gathers your data. It already does some sanitization before it sends this data, to this pre-processed data, to a aggregator, which could be some sort of server, right? An example of this is is Apple, right? So in Apple, what is happening is your phone gathers some local usage statistics, it sanitizes the statistics by adding noise, and then it sends it over to the Apple server, which aggregates this response from a lot of different users and then makes some sense out of it. Okay, and this is the kind of model that has been very useful in industry recently. And however, this kind of local privacy is very hard because the kind of guarantee that you are giving is that the probability that user A's value is T is almost equal to the probability that user A's value is S for any S and T in the domain, right? And so what this means is that you have to kind of make indistinguishable any two inputs in the domain which needs very high noise and as a consequence low utility. Okay, and the solution to this, of course, is that we are proposing in our work is a more fine-grained notion, right? So some applications may not need to. So for some applications, you may not need to blur every S and T in the domain. It may be okay to blur points that are close by according to some metric, and not blur points that are far apart, right? And a canonical example of this is what is called, is geo-indistinguishability for location privacy, which is actually a very special case of our, of our privacy framework. And there the idea is that, if you are hoping to get some location privacy and good ads, it is okay to blur the fact, you may not want your mobile application to know that, you are in such and such building, but it is okay for it to know that you are in La Jolla, right? Or for it to know that you're in the UCSD campus. So that's the kind of privacy guarantee that we are hoping to give. And that is the kind of privacy guarantee that we hope to give with profile-based privacy. So here the idea is that you have profiles which are a possible set of events that you hope to be kept secret, modeled by a distribution PI, right? So an example of this could be distribution of trajectories of people who travel from Berkeley Street A to San Francisco, right? And then the profiles, and then we have a profile graph where the nodes are the profiles and the edges represent pairs that are to be indistinguishable. So for example, if you're looking at this location example, you can have an edge between distribution of people who travel from street A to San Francisco, whereas and street B to San Francisco. So if you travel, so let's say you travel from street A to San Francisco, your neighbor travels from street B to San Francisco, you want you and your neighbor's trajectories to not be distinguishable, but it is okay to be distinguishable from somebody who travels from, let's say, Milpitas to San Francisco. Okay. And the privacy definition now is as follows. For all edges PIPJ, all edge pairs PIPJ in the edge set, the probability, and for all, your algorithm A satisfies this profile-based privacy if the probability that A of x pi is equal to y, conditioned on x being distributed from pi, and the probability that A of x p j is equal to y, conditioned from x being distributed according to pj. This ratio is at most e to the epsilon, where epsilon is a privacy parameter. Okay, so so what this means is that these profiles that are connected by each of the edges in the profile graphs would be indistinguishable. So if you get outputs from it, your sanitization algorithm is post-processing these outputs in a way that they become indistinguishable after the sanitization. Okay. This also has relationships to several other definitions. I won't go into a lot of details over here. So there are connections to what is called max leakage constraint hypothesis testing. And here the setting is similar, but the goals are somewhat different in the sense that the distributions, our distributions are public, but our observations are private, whereas things are somewhat different over there. After our work, there has also been some work on context-aware privacy, which looks at a very similar definition. Okay. So we talked about our definition. Now let's talk about some properties. So a very important property of privacy definitions is what is called post-processing invariance. And what this means is that if you take the output of an algorithm, which is epsilon private according to some distribution, and then you apply something to it, right, without going back to the original sensitive data, then your algorithm stays, then the output stays private according to the same definition. Profile-based privacy obeys post-processing invariance, okay, for any post-processing algorithm. Another natural property is what is called graceful composition. It is actually a big property for differential privacy. Here the idea is that if you take the same sensitive data and if you release something which is epsilon 1 private and something which is epsilon 2 private, then the combined effect of this is epsilon 1 plus epsilon 2 private. And I mean, basically the idea is that the combined effect of these releases does not give you does not give you really poor privacy, right? So the combined effect, the privacy decays gracefully, right? And there are a bunch of different versions of composition. So sequential composition says that multiple uses of the same data give slow privacy decay. Parallel composition means that multiple uses of different data leads to same privacy. For local inferential privacy, things are actually a bit more complicated depending on what things mean. And we have a few different, scenarios in our paper. In some cases, we can show that we get additive composition. In some cases, we can show that we get parallel composition. However, there are other cases where there is no composition result, and that happens when the profile selection process is kind of dependent across multiple trials. Okay. So we looked at, how to model fine-grained local privacy. We looked at some privacy properties. Now let's look at some mechanisms. And in our paper, we look at a very simple discrete setting, and we provide some mechanisms. The simplest discrete setting that we can think of is an edge profile graph, right? So the profile graph just comprises of a single edge, and the mechanism is to flip a certain bit x with probability p, with some probability p, right? And now the question here is how to pick p. If your p is very low, then you will get high utility, right? Because you are basically transmitting the same bit without any flipping, but it may violate privacy. Okay, and we can come up with a mechanism that will give us optimal utility in this case. So the way we formalize this is as a linear program. We minimize p subject to p greater than equal to 0, and as it happens, we can write down our privacy constraints that is implied by this kind of privacy definition. We can write these privacy constraints, and we can write them down in terms of linear constraints. So this gives rise to a linear program which you can solve, and solving this program will give you the optimal flip probability, and we call this the one bit mechanism. And we can also talk about, extending this one-bit mechanism. It's not, just confined to just single-edge graphs, but once we have a profile graph, we can talk about extending this one-bit mechanism to what we call the, one-bit cluster mechanism. We can expand this onto, clusters that we are showing over here, and we can basically expand this onto we can expand this onto any profile graph. It is just that the linear program, will still have a linear program. It is just that the linear program will have, a slightly more complicated structure. And then for categorical data, there is nothing sacred about binary data. We can also extend this to categorical data. The only thing is that we will need more complex privacy constraints. And our objective here could be the correlation, right? The correlation between what, you need an objective that measures how good the quality of your solution is. And the objective could be correlation between what you are outputting and what the input was. Okay, and you can solve it to get the answer. What about utility? Well, we will show you some utility plots, but we can actually also analytically analyze this for let's say the very simple one-bit case. So what we can show is for the one-bit mechanism, if for profile I the probability that x is equal to 1 is pi, and profile j it is pj, then for one-bit mechanism, your p will be at most pj minus pi divided by 1 plus e to the epsilon. Whereas if you had a local differentially private mechanisms which didn't take into account the fact that these profiles had different probability of pluses, then the corresponding local dp mechanism, the flip probability would be 1 over 1 plus e to the epsilon, right? So unless you have these pathological distributions where you're always where in one distribution you're always outputting 0, the other distribution always outputting 1, in that case it coincides with the local DP mechanism. But if you don't have this kind of pathological case, then your utility will be better. Okay, and again, here are some simulations on based on this. Again, this is the profile graph of two profiles. The local DP is the black line, and then we are looking at we have 3 values of profile 1. In one case, the profile 1, the probability of outputting a 1 is 0. That is the maroon line. The red line is when this is 0.25, and the gray line is when this is 0.5. And as we move the probability of prediction for profile 2, you can see what happens. Okay, and the observation is that again everything stays at least below the black line, which is the baseline local differential privacy, and then the utility increases or decreases depending on how close the profile 1 and profile 2s are. Okay. So in conclusion, we present a form of inferential privacy for the local setting, and we look at mechanisms which have better privacy utility trade-offs. And there's been other follow-up work in this setting. For example, context-aware privacy is a recent work by some people from Google. And this is mostly work by my student Joseph Genlich. We had a paper on this at ISIT 2019. It's called Profile-Based Privacy for Locally Private Computations. And the paper is available on arXiv for all of you to see. Okay, and with this, I will thank you all for listening and end this talk.